All right, hello, General Chemistry Nation. Thank you so much for joining me in this, I guess you could say, very long conversation of the first part of general chemistry. And so that's where we're going to start, is really just be like, okay, well, what, is chemistry? Well, chemistry is really the only thing that matters. This is the study of matter. So all around us, everything that we touch, we feel, we see, right? These are all forms of matter, and things that we actually can't see as well. Matter basically has two qualities. It occupies space and has mass, right? It has a weight, I guess you could say, attached to it. So that's where we're going, right? We're going to be talking about chemistry study of matter. And what is matter? Well, it's something that occupies space and has mass, which is basically everything in our tangible realm around us. So there are three phases of matter, and we could probably say them all together in unison right now as far as solid, liquid, and gas, right? So those are the three phases that we actually have. So let's just take a moment and just talk about them in a very, kind of general sense. With our solid phase. And so with the solid phase, basically we have, a couple things, atoms, and we'll get into atoms, right, soon, but atoms of a solid are basically very closely packed together. This is like a 3D lattice. If you go to some gardens, right, you have a lattice where the vines can grow up through the lattice and show their flowers. Well, now take that kind of flat lattice and expand it into 3 dimensions, and now you have kind of that solid phase idea. So the atoms are very closely packed together. There also is the fact that they have a defined volume. So those are two aspects. And as far as the defined volume is concerned, right, if you have a solid material, such as this just little, brick here that we have, that it has its own volume, right? Depends on the shape of the solid. And so we could even have that solid, in some type of flask or some type of beaker. Right? And so it has its own defined volume. Now, that's a little bit different from now the second phase, which is the liquid phase. Here we could say that, atoms, of a liquid have room to move. Our solid state, we could also define, as a static state, right? Saying that atoms are not moving, but that's not quite true. There are vibrations and things of that nature that are going on. So technically the atoms are moving in the solid state as well, but they're really not moving a lot. And so we have that set volume. Liquids now, they do have a lot more ability or room to move. So the elements are a little bit further apart from one another as opposed to being closely packed. And what I kind of like to look at with that idea is that these, atoms have the ability to roll over one another. So because of that idea, liquids take up the shape of the vessel. So they still have a standard volume, or still have a set volume. They just take up the shape of the vessel as opposed to solids, which don't necessarily take up the shape of the vessel. So if we had our, beaker, again, I know my drawings are fantastic. You'll get used to this. There's our beaker. Right, and so we have a set volume within there. But it definitely takes up the shape of the vessel, meaning that I could turn the vessel, if you will. And so now my volume would look something maybe more like this. Right? It's the same volume, but it's just taking on the shape of the actual vessel. So you could almost imagine these are, molecules, elements rolling over top of one another as far as that idea is concerned. And the last phase is the gas phase. Gas phase these atoms have a wide range of motion. They are moving all over the place. So that means there's actually lots of space in between atoms. So it's like a hierarchy. We went from solids where they're closely packed together, and then we went to liquids. Well, they're close, but they're definitely further apart because they can roll over top of one another. And now we enter the gas phase, where now we have basically a lot of space in between the atoms. And so when talking about volume, the gas phase takes up the entire volume of the vessel. So if you have your beaker, now you're talking about these gas molecules being evenly distributed all about the actual volume of the vessel that they're contained in. And there's a lot of dynamic motion. There's lots of movement. So that gives, one special feature of gases. Is that our gases are compressible. That's getting into the idea of pressure. So we have, these three distinct phases: solid, liquid, and gas. Our solid state is where everything is closely packed together and they take up a rigid volume. We then have the liquid state, which is a little bit looser, so the molecules have a little bit more space, elements have a little bit more space, and so they can tumble over or roll over one another in defining their shape of the vessel, or with the vessel, rather. And then finally gases, which just take up the whole volume of the vessel. And now we find another property, or at least something different between the other two, which is the idea of pressure, the idea that since there's all this empty space, we can actually compress gases or expand gases, and that'll become very important in subsequent sections. Matter can be further subdivided as far as between those states that we've talked about already, solid, liquid, and gas, but just as far as talking about, matter, we can further, break it down. And when we look at matter subdivisions, there are two to start off with. We have this idea of something being pure, or we have this notion of, a mixture. So, for something that is pure, basically we're talking about, a molecule or an element that, basically is not contaminated or does not contain other different molecules and or elements. So that's the pure state, right? We could talk about that in a couple different examples, right? As far as Here we have iron in the solid state. And we see that solid state from the little s. Right, so this would be a pure element. There's other examples as well. A lot of the metals tend to be monoatomic. These are things that we'll get into as our conversation continues. The element oxygen actually exists as a diatomic. And it's actually in the gaseous state. So we see that little G for that. And again, this would be then a pure element. We'll come to learn there are different styles of these elements as far as monoatomic or diatomic types of elements. That's coming in the future. We could also look at a molecule or a compound. And so here is, something I'm sure we're all familiar with, right? This is water. And it's actually in the liquid state. So we have the little L, the little cursive L. And this would be a pure molecule. So if we're just talking about, one entity, whether that be elemental or molecular or a molecule, if it's pure, there won't be anything else that's actually in there. That takes us to then the second part of that subdivision, which would be looking at now mixture. And basically a mixture is a combination of more than one type of molecule or element. So basically we have, more than one. Within this, there are two different distinctions within mixtures, just like we could have, elements being pure or molecules being pure. We have two different types of mixtures that could occur. And so one type of mixture is homogeneous. And this is basically a mixture that cannot be determined it is a mixture by visualization or heterogeneous, which is a mixture that can be determined. By that visualization. So you have two different terms, homogeneous. Basically, the idea is it cannot be determined. It's a mixture, and that's just by plain eyesight. With heterogeneous, this can be determined as far as being a mixture. And so as far as an example of these two, if we put sodium chloride or salt in water, right, the salt dissolves, and you can't tell it's a mixture. Specifically by eyesight. Obviously, you could taste it and taste it's salty. Not that you should be tasting your chemicals, but that's the idea. You can't see it visually, and so that's our homogeneous solution. Secondary example would be looking at maybe oil in water. I know that we're not maybe up to speed with oils and hydrocarbons and forces of attraction or anything like that, but with oil and water, the oil clearly floats. On top of the water. This can be seen by eyesight. So that is our heterogeneous type of mixture. So those are our two terms for our mixtures. We have homogeneous and heterogeneous. And one we can't tell it's a mixture by eyesight, homogeneous. One we can tell it's a mixture by eyesight, and that is heterogeneous. So basically, our homogeneous mixture will look something like this. We had now maybe a beaker. Right, and so we can't tell it's a mixture. And then we have the heterogeneous. And so we have roughly our same beaker. We could say that, well, there's a phase difference in terms visually. We can see with one layer and another layer that's actually there. And so we can tell it's a mixture. So this above would be our salt water example, and below would be our oil water example. So those are the different subdivisions, or different subdivisions, for matter. We have, things that are pure, namely molecules that can be pure, like water, oxygen gas, pure. We can, in terms of the elemental state, we can have, iron as well, solid state, right? Those are the examples that we did earlier. We also talked about then mixtures, mixtures being homogeneous or heterogeneous in terms of whether we can visually see whether there's a mixture or not. The last bit of kind of this, introduction into just a general term of chemistry is the notion of physical and chemical change. And with physical change, we're looking at, a change in phase. Another way you could say this is appearance. But we are not changing the composition. Which is, the element or molecule. So the physical change, we could look at maybe like ice, right, going to water, right, we're talking about melting there, right, that's just a phase change. We could go even further to, steam. As far as, water or H2O now in that gaseous state, where it gets vaporized. Right, so these are all examples of physical change. Chemical change is basically looking at a change in the structure of elements and molecules. We're basically looking at the idea of just breaking and or making of new bonds, breaking of bonds between elements and molecules to construct new things, right, or new molecules. So we have physical change. We're not breaking anything up. chemical change, we are breaking things up and we're forming new things as far as new molecules. We can break elements down, we can break molecules down, and then form, basically new molecules from that idea of chemical change. An example of chemical change would be looking at like a reaction. Where if we take propane and oxygen, we can react them according to what's known as a combustion reaction. Right, just like on your grill. Cooking up some chicken or steak, right? We're doing a combustion reaction where we're combusting propane with oxygen to produce CO2 gas and H2O. And we're not there yet, but we would need to have some balancing of the process. So we would need 5. So there would be an example of combustion reaction. We're actually physically breaking things down. Our propane has all these chemical bonds between hydrogen and carbon. Oxygen has its double bond as well. And now we're making new molecules such as carbon dioxide and water. And so we've made now new bonds between the elements. We've undergone chemical change. Now we have carbon bound to oxygen as well as hydrogen bound to oxygen, right? And so there is our very nature of chemical change. With the whole notion of making bonds and breaking bonds.